Hello, good evening. Can you hear me? And can you see my screen?
Yes, sir.
Okay, we'll start then. Um, Last week's lectures were about capacitors, and this week we'll mostly have what happened. This week we'll mostly have questions on inductors and capacitor inductor circuits. Now, okay, have you gone through or watched the lectures of this week? Yes, no, I need an answer. If no, then please say no. Deepak, have you watched the videos of this week? Deepak, are you there?
Yes, sir. Sir, I saw only two lectures, sir. 31, 32.
Mm-hmm. What, 30 and 32?
Lecture number.
Okay. So both of you, I'm asking, do you have any doubt from the lectures of this week or previous weeks? Okay, I see that you can understand everything. All right. So before we start today's lecture, we'll solve some problems. Many of them are kind of transient problems, but let me remind you that the way that we will solve these problems today are not very mm, elegant elegant way of solving those problems. But since you guys have not yet learned how to apply differential equation in circuits, means you can, but there is much easier ways to do that. So we'll go through, I mean, we'll use those non-elegant methods only. We'll mostly look at mostly try to think about initial and final conditions of the circuits, and then try to derive a transient equation from that. So the basic concept behind that we will mostly use is this. Now suppose you have some function f, which is a function of time, and we know that it's an exponential function, and it goes like this. Okay? We know that the final value is, let us say, f1. Now can you express this one? Say the time constant is tau, that is known to me. Can you express this one as a function of time? What is the equation of this then? Can you tell? Rishi, can you tell what is the equation of this curve? Deepak? Deepak, can you tell what is the equation? Rishi doesn't even bother to talk or unmute.
Sir,
I couldn't hear anything from you anyway. So this kind of equation is expressed by f1 uh, e to the power minus t by tau. How to verify that? That if I put t equals 0, then no, sorry, I'm wrong. If I put t equals 0, then what we will get is ft equals f1. But that is not the case, right? At t equals 0, it was 0. So it has to be f1 times 1 minus e to the power t minus tau. Now if you write like this, I will see if I put t equals 0, then it's 1 minus 1, so ft comes out to be 0. And if I put t equals infinity, e to the power minus infinity is 0, so what we get is ft equals f1. So this is the way to check that what you have written is correct. I wrote it wrong initially, but I checked it is wrong. Now this is exponential increment, and the other one is exponential fall. Exponential fall looks like this, and say the initial value is f1, it's ft versus time. So this one will be what I wrote earlier by mistake, f1 e to the power minus t by tau. Tau is time constant. Here also, if you put t equals 0, you get ft equals f1 because e to the power 0 is 1. And if you put t tends to infinity, you get ft e to the minus infinity is 0 equals 0. Now, these are the simplest cases. Sometime we will, like today's class only, we will encounter some problems where we will see that it doesn't start from 0. Say it starts from some other, say some other initial value and ends at some other initial value. So let us say this one is f1, starts from f1 and ends at f2, f2 and t. This one is nothing but a shifted version of case 1. If I mark them as case 1, 2, 3, this one is nothing but a shifted version of case 1. So what we can do is we can remove the shift. If we remove the shift, it becomes like this. And what is the final value? Final value becomes f2 minus f1 because we have simply subtracted f1 from all the points. Now for this, we know the equation. From the first case, we can write it is f2 minus f1 to the power minus t by tau. For this, we know. Now once we know this, we can now add the shift, right? So if you add the shift now, it becomes ft equals, so the shift was f1 plus f2 minus f1 t by tau. So this is the expression for this. If you want to cross check, you can put t equals 0. If you put t equals 0, then what you get, ft equals f1 plus f2 minus f1 e to the power 0 is 1, so 1 minus 1, so what you get is f1. Similarly, if you put t tends to infinity, what you get is ft equals 1 minus 0, so f2. So this is a way of getting. Now always remember that there is one assumption here. Assumption is we know that these curves are single or first order equations which are rising or falling exponentially. Then only we can apply this. Just do not always look at this. Can be a parabola also. Parabola also looks more or less like this. Just by looking at it by visual inspection, you cannot distinguish. Okay, so I know that it's exponential, that's why I can write like this. Now similarly, if I write the case 4, we'll just look at the decay. So it is like this, that it decays from some value decays from some value but doesn't reach zero. Doesn't reach zero. It started decaying from f1, but it becomes steady at f2. It can happen in some cases, right? And the time constant is again tau. How to do that? Now again we will give a shift or remove the shift, sorry. Once we remove the shift, it becomes like this. Starts from f1 minus f2, right? Because here the shift is f2. We are simply removing this much of shift, DC shift. You know, f1 minus f2. Now this equation we know. This equation is f1 minus f2 e to the power minus t by tau. Now for this one, the actual one, we can write ft equals, we don't now just add the shift, f2 plus f1 minus f2 e to the power minus t by tau. Now similarly for this case also you can verify that if you put t equals 0, what you get is f2 plus f1 minus f2 e to the power 0 is 1, so times 1, that comes out to be f1. So t equals 0, it's f1, matches. And if you put it tends to infinity, steady state, ft, sorry, ft equals f2 plus f1 minus f2 times e to the power minus infinity is 0. So what you get is f2. Both of them match. Now, why I am doing this is today there are several problems where you are not asked to find out the steady state values, rather you are asked to find out expression of the current or voltage through capacitors and inductors. But we have not yet gone through solution of those circuits by differential equation. They're actually done by Laplace transform, by transferring the circuits to Laplace domain. It's not the only way, but that is a much easier way to do that. Once you transfer, it becomes like a regular circuit to solve. And then inverse Laplace transform is nothing but solving a differential equation. That's the way we solve complex circuits, circuit transients. But since that is not yet taught to you, here we will do like this. When we are asked to find out the expression, or when we are asked to the value at certain point, we have to find out the expression. So we'll find out the initial value and the final value, and we know how the pattern is, whether it is rising or falling, and write the expression using the formulae that we just derived, and then do whatever we have been asked to do. Okay, I know there is no question, or if there is any question we can ask. So in the circuit shown in figure 1, determine the value of it at t equals 2 second. Now it's a simple RL circuit whose equation is given by Vt. I will not write them as function of t. When I am writing it as a small letter, that means it is instantaneous, it is function of t. Okay, so what we have is V is equal to IR plus L di dt. Initially relaxed, so initially maybe there was a switch which was initially open. Now that is closed at t equals 0. Right now the expression of V is given by this 4t. 4t is higher. There is V is increasing linearly with time. If I draw the voltage graph, it looks like this. At t equals 1 second, the voltage is 4 volt. What kind of waveform is this we discussed last day when it increases linearly with time? Okay, it's called a ramp. All right. Now this is the one. What we have is now two things, two variables I and t. We have to solve this equation. So we can write 4t dt equals IR dt plus LDI. I we do not know as a function of time. So what to do? Wait. Thing is, this is the, if you write like this, okay, IR, this is 2i, I put the value of I and value of L, so 2i and 4. Now if you can rearrange it like this, IT plus, sorry, I'm again writing like this, half I plus DI dt equals T. This is a standard form of differential equation where you have to find the integrating factor like this, e to the power integration half dt, which comes out to be equal to t by 2, and then you multiply both sides with this integrating factor. So you can solve this problem. I'm not doing this. Finally, what we'll get is from this it as a function of time 2t minus 4 plus k e to the power minus t by 2. Now this k is the constant of integration. How do we find out the value of the constant of integration? We find it out from the initial conditions. So what is the initial condition? Initial condition was that there was no current. So at t equals 0, I was equal to 0. Once we put that, we get is 0 equals 0 minus 4 plus e to the power 0 is 1 k. So k equals 4, right? You have yeah, have you studied Laplace transformation?
Yes, sir.
Okay, so you know how to solve differential equation using Laplace transformation.
Yes.
Okay, so you can do solve them in that way also. Anyway, it hardly matters how you solve. You will get the same thing at the end. And so once you get the value of k, the integration constant, we can write current as 2t minus 4, 1 minus e to the power minus t by 2. This will be the expression for current in a RL circuit where the voltage is increasing in ramp. Now the question is, what is the value of current at t equals 2 seconds? Now you simply put t equals 2 and you will get I, not IT, I at t equals 2 second as somewhere close to 1.47 ampere. So this question is all about solving this equation. Okay, we'll go to the next question. So the same question, like the last circuit only, we have been asked to find out the inductor voltage. Now we know the current expression, so all we have to do is V is L di dt. So all we have to do is solve the differentiate the current expression. So once you differentiate the current expression, what we will get is, so I will write 4 times ddt of, what is the expression? Yeah, 2t minus 4, 1 minus e to the power minus t by 2 4 times, so ddt of 2t becomes 2 minus 4 times 1, minus of comes out, so it becomes plus of e to the power minus t by 2. Wait, oh, this one will be removed, is differentiated. So it becomes 2 minus 2 e to the power minus t by 2. It is 8 times 1 minus e to the power minus t by 2. Right, this is the expression for voltage. And now if you put t equals 4 here, you will get the voltage value at 4 second. You put t equals 4, you get VL. Some 6.9 volt should come. Okay, we'll go to the next question. If you have any question, you can stop me and ask. Constant current source is supplying 15 ampere to a circuit shown in figure 3. The switch S, which is initially closed for a sufficiently long time, is suddenly opened. Obtain the complete time response of the inductor current. Okay. Now, you see, we have to first find out the steady state condition. What is the steady state? Like, what was initially switch was sufficient initially closed for a sufficiently long time. Now it's a current source. So if this switch is closed for a sufficiently long time, how much current will flow through the inductor and the resistor? We discussed these things: voltage source, current source. Okay. If it is short circuited, then the voltage here is 0. This voltage is 0. So there is no way that any current is flowing through the resistance. Right? Now, there is a thing here. There are one inductor and one closed switch in parallel. One inductor and one closed switch in parallel. If there is 15 ampere current flowing from the source, the whole current can flow through this 15 ampere also, this inductor also. The whole current can flow through this short circuit also. And they can share also at, in many possible ways. There are several possible answers here. Because if there is a constant current through an inductor, there is zero voltage across it. So there is infinite answer to the steady state problem of this, but we will assume that this should have been mentioned in the question. We will assume that the whole short circuit, the whole current is flowing through the switch, the short circuit. But this is not the only solution. There could have been many ways. Say, for example, I show you something. Say, for example, if I draw, the resistance is out of the question, that there is no doubt about it. Say, for example, it could have also happened that some 10 ampere is going through the inductor in the other direction. 15 ampere and say some 25 ampere is coming out. This is also possible. There is no rule of electrical engineering that would stop this from happening, right? This is also equally feasible. So you don't know the initial current through the inductor, but from the, since there is no other information, we will take that the switch was carrying the whole current and the initial current through the inductor was 0 ampere. That is, there was no energy stored in the inductor. Now, initially closed for a sufficient long time and is now suddenly opened, obtained the complete time response of the inductor current. Now, this is one of the question. Generally, what we do is, if we are solving this kind of, we transform this to the Laplace domain where the 15 ampere current becomes 15 by S. Resistance remains as it is, 6, and the inductor 3 Henry becomes 3S. Now we solve it like a regular circuit. So 6 parallel to 3S, that is 18S by 6 plus 3S is 6S by 2 plus 3S. Sorry, 2 plus S, like this. So this much is the resistance and the current is flowing. In this way we solve. But here we're not going to do that because we are not studying about transient as such. What we will do is, initial value we know, initial value to the inductor current we know. We'll find out the final value to the inductor current. So to do that, what we have to do is we will draw the circuit once again. Use 15 ampere, 6 ohm, and inductor 3 Henry. Now, what is the final value? You see, at steady state, what will happen is the whole 15 ampere current will flow through this inductor, whole 15 ampere, and there will be no voltage across, no current across the resistance, hence no voltage. At steady state, inductors, like if you have a RC network and you are asked to find out the steady state condition, what you can do is you can replace the inductors by short circuit and capacitors by open circuit. We discussed this thing last time. Now you can verify this also. A 15 ampere constant voltage is, sorry, constant current is passing through an inductor, and inductor voltage is given by LDID. Resistance also, you see, the voltage is 0. So these two elements are in parallel, so their voltages must be same. So KCL and KVL are all matching. So the whole 15 ampere current will flow. Right now, we know that the initial current through the inductor was 0, and the final current was 15 ampere. 0 ampere is IL, function of t. So we can directly write from here that IL is 15 times 1 minus e to the power minus t by tau. Only thing we have to find out is how much is the time constant. Now how to find the time constant here? Time constant as seen by this inductor. So what we have to do is we have to open circuit this current source. This we discussed, why we open circuit current source and short circuit voltage sources. Once you open circuit the current source, the equation, the circuit becomes like this. Becomes like this. L and R, simply RL circuit, RL series circuit it becomes. Right? Now for this thing, what is the time constant? Time constant is L by R. L by R is 0.5. 0.5, say half. So now if I substitute tau here, what I get, tau is half, so e to the power minus 2t. So this is the expression for the inductor current. Okay. This is it. Okay, we'll go to this question. In the circuit shown in figure 4, the switch S1 is initially closed and S2 is open. The inductor carries a kind of what is it? The S1 is initially closed and S2 is initially opened. Okay, so we'll draw the circuit how it was initially. Just draw it here only. This is a resistance, the 10 ohm resistance. S1 is initially closed, so short circuit, and inductor here. S2 was open and 100 ohm resistor here, capacitor 10 volt, and the inductor was carrying a 12 ampere current in this direction. And the capacitor was charged in this fashion. Now let us see whether this circuit in this state was at steady state or not. If you look at the capacitor, yes, it is at steady state because it has no way to discharge its voltage or the charge that is had stored in it. So the capacitor will keep on holding this 10 volt. Also look at the inductor. The 12 ampere current that it is carrying is going through this switch. It's an ideal switch, no resistance. So the energy stored in the inductor also is constant. It is not changing. We know. So the circuit was initially a short circuit, a stay at steady state like this. Somehow this state was achieved. Now the question is from here, S2 is closed at t equals 0 minus and S1 is opened at t equals 0. Now the circuit has changed. What they have done is S2, this one they have closed and this one they have opened. The current through C voltage across cell at t tends to 0 plus. Now here you see, whenever you are asked to find out in such question what is the thing at 0 plus, such a question is solved in the last class also. We assume that we are being asked about the state right after the circuit is changed. Now inductor current cannot change suddenly, capacitor voltage cannot change suddenly. So we will assume, so we can take the inductor current as a constant and the capacitor voltage as a constant for we can replace with a constant current source like this, and the capacitor we can replace the constant voltage source like this. Okay. Now we'll complete the rest of the circuit, and they are saying S2 is closed, so this is joined, and S1 is open, so the short circuit is no more present. What we have is this resistance here. Yes, 10 ohm. Oh, there was one 10 ohm there, not 100. You guys are not saying anything. I wrote 100 in terms of 10. Did you just copy it in your copy? God knows what you are thinking. So 10 ohm and 10 ohm. We have been asked to find out what happens at t tends to 0 plus. That means we can simply solve this circuit and tell. So this one we can call, say, initial condition circuit or something we can say. This is not a standard terminology or something. Just we are calling this like this. Okay. Now this one we have to solve. And we have to find out how much current through C and voltage and L. So basically what we can do here is we can simply we can just apply a load analysis here quickly. So currents going out, we will find out V by 10 is the current going out and minus 12 is the current going out, and V minus 10, that is V plus 10 by 10 is the current going out. That comes out to be 0. Now V by 10 gives us V by 5, that is equal to 12 minus 1, 11, 55 volt. Now if V is 55 volt, that means the initial voltage right after this switching is done across the inductor is 55 volt. And how much is the current through this? So we got that 65 volt by 10. So initial current to the capacitor is 6.5 ampere. There is no source energy source in this circuit, so and there is resistance also. So definitely both the current and the inductor voltage are going to die down to 0 after some oscillation. Okay. The next question: in the figure shown, the ideal switch has been open for a long time. If it is closed at t equals 0, then the magnitude of the current in milliampere to the 4Q, how much? Okay. So what we will do is same thing. We'll first see what happens if the ideal switch is open for a long time. So you can simply ignore. So we will look at the circuit and we will ignore this switch. This is not there at all. This branch is not there at all. And it is capacitor here. So at steady state, what will happen? There will be no current through the capacitor, but it will hold some voltage maybe. So basically what happens? Oh, there is a inductor also. It is will be at a short circuit at steady state. So basically, just before the switch was closed, the circuit would essentially look like this. Inductor is short circuited, capacitor is open circuited. Oh, there is one more resistance. Sorry, capacitor is here, open circuited. Now this is 10 volt, 5k, 4k, 1k. So 1 unit of drop, 5. So this must be 5 volt. So the capacitor was holding 5 volt. And how much current? 10 volt by 10 kilo ohm. So 1 milliampere. 1 milliampere current was flowing in the inductor like this, right? Now the question is, switch is closed at t equals 0, then the magnitude of current through the 4 kilo ohm resistor at t equals 0 plus. So now we have to do the same thing. We'll replace the capacitor by a constant voltage source and the inductor with a constant current source, and the values of the voltage and current sources will be what we found for their steady state value at the steady state. Now we will draw the circuit once again. This is 10 volt, 5k, 5 volt. Sorry, just getting. And 4k. This one is closed, right? Let me just check the question once. Closed. One K and 1 milliampere. Now, like as always, we will take this one as 0 volt. Now, if this is 0 volt, since the switch is closed now, this is also 0 volt, and the 1 milliampere current simply completes its path in this loop. Completes its path in this. It doesn't go to the other side of the circuit. Now we are asked to find out what magnitude of current through this. So this current we have to find out. So we can simply apply KVL here and we can find out. Just looking at this, we can say that the voltage across the 4K resistance is 5 volt. Right? This voltage is coming 5 volt. So the current IT at t tends to 0 plus is 5 volt by 4 kilo ohm. That will be 1.25 milliampere. Any question till now? Okay. Now these questions are a bit tricky and I am a bit skeptical about these options here. I don't know. So not everyone, not all of it might be correct. We will see. Again, we have to, the switch has been in position 1 for a long time. What kind of switch is this? Quickly tell. We discussed last day. Okay, very good. So this, I don't know why I discussed, but this switch is called single pole double through. Anyway, the switch in figure 6 has been in position 1 for a long time and is then moved to position 2 at t equals 0. Let us draw circuits. Okay, I think that is all we can do. So it was in position 1 for a long time. $25K. Now, steady state, inductor must be short circuited, right? Means at steady state, short circuited means there might be current through it of any amount, but there must not be any voltage across it. Obviously, DC circuit, if there is a DC current through a inductor, the voltage will be 0. So definitely this 20 kilo ohm was not carrying any current. 20 kilo ohm was not carrying any current because it is parallel to the inductor. So the voltage across it must be 0. So what we can do is we can simply replace this 20k and 5 Henry inductor combination as a short circuit. Simply replace it with a short circuit. And this is 50k. Right? It was like this. And capacitor. This was open circuit, completely different from it. See, this ut is called an unit step function, which steps at t equals 0 ut. Similarly, if you want to give a step at some other point, what we call is just shift the origin. Say if you write ut minus 5, that means it steps at t equals 5. T equals 5. Okay, it is possible to uh, synthesize various waveforms using the step function. Say for example, if you have a pulse like this, say a pulse like this one you can break into two. One is something like this, another one is something like this. So it would become ut plus, or not plus, minus ut minus a 2. This will give you this pulse. Anyway, so now the question here, you see it's written u minus t. U minus t basically means minus ut. It's a odd function. Okay, it's minus ut. So basically, what we will simply take that as soon as t equals or at t equals 0, this voltage source becomes active with a polarity like this, 10 volt. Okay, but before t equals 0, this voltage source was not active. Now when we are talking about that the switch S was at position 1, this voltage source was not active, so we need not now draw this half of the circuit. Anyway, there was no current in on that half. We'll simply find out how much voltage the capacitor was holding. It's 50k, 25k in this fashion. So the capacitor was holding a voltage of 60 times 50 by 75, so 40 volt. 40 volt. So at steady state, this capacitor was holding a voltage of 40 volt. I'm sorry, why did I write 60 here? 6 volt. 4 volt. So it's holding a voltage of 4 volt. Another question is, it is then moved to position 2 at t equals 0. Determine Vc and IL. So now we will go through the same process. We'll redraw the circuit, or let it be here. Let me copy this. Oh, and draw. Okay. Now 4-volt capacitor, as usual, we have been asked to find out t tends to 0 plus. So we'll replace it with a 4-volt source. So this becomes a 4-volt source. And the inductor, how much current was the inductor carrying? The inductor was not carrying any current at all because the voltage source was not active. So basically, the inductor is a 0 ampere volt current source, and here is a voltage source of 10 volt this way and 1k. 1k. This. Now, a 0 ampere current source is nothing but an open circuit. Okay, just an open circuit. The question is initial capacitor voltage, initial inductor current. If initial capacitor voltage is 0 volt, initial inductor values of inductor currents here, and none of them are 0. But it is not possible because at t tends to 0, inductor current was 0. At t tends to 0 plus, inductor current can never be some finite value because that would require infinite voltage across the inductor. I don't know whether you can appreciate that. Because V equals LDIdt. You should actually, because we discussed this. So if a sudden increase of current would require infinite voltage, that is why you called that. That is why we say that inductor stops resists sudden change in current. So the final answer is capacitor voltage is 4 volt and inductor current is 0 ampere. Now the next question, if you see it's the same circuit, we'll just copy, but something else we have to find out. We have been asked to find out the dV dt of the capacitor. Now this was the capacitor, if you remember, this 4-volt branch was the capacitor. Now for capacitor we know that I is C dV dt, current is C dV dt. So we have been asked to find out derivative. Basically we have to find out the current in this condition and then divide the current by the capacitor value, capacitance value. So you have to solve this circuit to find out this current, I. Okay. Now let us see whether we can solve it in an easy fashion. Okay, I will remove this thing so that it looks cleaner. Now this is 4 volt. This is also 4 volt. Now if this is 4 volt, what is happening? Some current is flowing in this direction. Is 4 volt. So let us find out how much current is flowing in this. It is 2 by 25 milliampere. 6 minus 4. So 2 by 25 milliampere. Oh, sorry. One mistake I have made here. This is open circuit. The switch has been thrown from position 1 to position 2. So the capacitor is no more connected to this side of the circuit. This is open circuit. So the capacitor is no longer connected to this side of the circuit. So this is open. So now our job is made much easier. So we have 4 volt. Is that possible? Yes, that is possible because there is a resistance here. So basically what we have is uh, 4 volt and 10 volt voltage sources are in series. So this one becomes 14 volt. 14 volt. So how much current is flowing to the capacitor? I will let IC. IC is 14 volt by 1K, which is 14 milliamps. Now dVdt is simply this I 14 milli by the capacitor, which is 20 micro. So it becomes 14,000 by 20, which gives us 700 dVdt, so volt per second. Now, oh, here is a thing. Look carefully that we have taken the I in this direction, but in the question, the VC polarity is given like this. So if we have to preserve these polarities of I and VC, what we have to write is I is minus of C dVC dt, because the current is flowing from the negative to positive terminal through the capacitor. So if that is the case, so one negative value comes here. So our answer becomes minus 700 volt per second. And that is understandable. Should that be the case? Yes, that should be the case because the circuit is going towards steady state, so the capacitor voltage should drop here. And finally, there will be no voltage in the capacitor at all. We'll look into this question. We have 3 more. In the circuit of figure this, the switch S has remained open for a long time. Okay. So if the switch is open for a long time, we need not consider for the, I mean for t tends t less than 0, we need not consider this part. And what we have is a 2 ampere current source here. At steady state, what happens? No current through the capacitor. So 2 ampere was completing its path here, and it was creating a voltage drop of 10 volt. So definitely V0 with the given polarity in the question, V0 at t less than 0, steady state obviously. So better to write like this, was 10 volt. 2 ampere was flowing. Now the switch is closed instantaneously at t equals 0. Determine V naught at t equals 15 microsecond. Right? Now see, we have been asked to find out the voltage at certain time. That means we have to find out the transient equation. We'll see how to find the transient equation like we as we already seen. But for that we have to find out initial and final values. Initial value we know, 10 volt. Final value we have to find out. Let us see what should be the final value. So let us draw the circuit. after the switch is closed, 25 volt, 10 ohm. So we are trying to find out the final value. So once again, this capacitor will be open circuited. Means there was a steady state before the switch was closed. The switch is closed, the circuit goes into transient and again gradually approaches steady state. Okay. Five ohm, 12 ohm, 2 ampere. So what we have to find out? We have to find out this voltage. How much voltage this is at of this circuit simply. Now what we can do is we can yeah, we can apply node analysis. That will give us V minus 25 by 10 plus V by 5. This one, V by 5, this one equals 2. Yeah. So what we have is V by 10 plus 2V by 10 gives us 3V by 10 equals 2 plus 2.5, 4.5, so 45 by 3, 15 volt. Right? So the final value is 15 volt. So now we knew that the initial voltage across the capacitor was 10 volt. 10 volt it had, and that increases to become 15 volt steady state, the next steady state. Okay. So we have seen how to find out the equation of this kind of thing, this kind of curve, because capacitor. Now time constant means we have to replace the voltage source. Sorry. Replace the voltage source with short circuit, and so this is the capacitor staying here, and the current source with open circuit. Now if you do that, the circuit becomes like this. So basically this 10 ohm and this 5 ohm, they come in parallel with the capacitor. So the resistance that we have here, obviously not from this, do not think it is from this, the time constant resistance that we have here is 10 into 5 by 15, to be 8.33 microsecond. Now we will look into it. How was the equation that we derived some time back? This one. It was initial plus final minus initial times that one. So it should be, so the voltage should be initial plus final minus initial, so 5, e to the power minus t by tau. Let us check once. If I put t equals 0, no wait, what did I write? Am I doing something wrong? T equals 0. Oh, it is 1 minus e to the power minus 1 minus e to the power minus. Or we can simplify it and write 15 minus 5. This. So this is the equation of the voltage. That is, initially the capacitor voltage was 0 volt, the switch is closed, capacitor voltage goes through another transient and reaches 15 volt, and the transient is governed by this equation. Now you have to find out the capacitor voltage at t equals 15 microsecond. So what we have to do is V at 15 microsecond is 15 minus 5 times e to the power minus, that is 8.33 microsecond. So T by whatever you find, that will be the answer. It will be around 14.17 volt. Okay, any question in this problem? Okay, we'll look into the next question. Same thing. Obtain an expression for IT at t greater than 0. The circuit was initially relaxed and the switch S has been closed at t equals 0. See, when we say the circuit was initially relaxed, that means the circuit was initially at steady state. Why I am saying this is there was an argument that is the circuit is initially relaxed means there is no current through the inductor, but that cannot be a case, right? Because there is a current source parallel to the inductor. So, and a DC current milliampere must be flowing through this inductor. Then only we will get a steady state, because we have a DC current across the inductor through the inductor. That means the inductor voltage is 0. And the inductor voltage is 0 volt and no current or voltage through the resistor. And on the other side of the circuit, this 100 milliampere is completing its loop like this. Okay. Now we are asked to find out the voltage and current through the current through the resistor. Now you see, inductor voltage and current we can find out, like initial value, initial voltage, final voltage we find out, and from there we can find out the time, and we can also find out the time constant and find out the voltage. But the time constant and all those concepts do not hold for the resistors, right? Or so we cannot find out the initial and final current through the in and of the resistance and then solve the circuit, because we cannot find out the time constant of the resistance, right? Although the time constant of the whole circuit is the same, but we have to do it from the voltage across the inductor, which will lead us to the current through the resistor. Now initial current we know it's 200 milliampere without any doubt. What is the final current? What is the current after we close this switch? Okay. What we can do is This 30 ohm 100 milliampere combination, this combination 30 ohm in parallel to 100 milliampere, this we will replace with a voltage source in series with a resistance. So the resistance will be 30 ohm and the voltage will be 100 milliampere times 30 ohm, which would be 3 volt. We'll replace with this. Now once we have this, we can complete the this 3 volt, and there could have been an easier way also. We need not solve the circuit. Let us do it in an easier way. We need not replace this. What exactly what we have, we will draw like that, and we will see whether we can solve it in an easier way. So what we have is current source here parallel to some resistance, another current source, again some resistance, and an inductor. So without solving any equation, we can simply say that if there is 100 milliampere current here and 200 milliampere current here, at steady state, there must be 300 milliampere current through the inductor. Any doubt here? It is the same way we solved the other half of the circuit before the switch was closed. No other way for the steady state. The steady state, the inductor is short circuit. So the whole 300 milliampere current must be flowing through the inductor. So basically now what we have is the inductor current sorry inductor current started from 200 and reaches 300 after the switching is made. Now we can write the inductor current equation like the same. It's initial plus final minus initial. So inductor current IL will be 200 initial plus final minus initial, so 100, 1 minus e to the power minus t by 2. I think we could have simplified that. So it becomes 300 minus 100 e to the power minus t by tau. All of them are milliampere. Okay, let me make it simple so that we do not make a mistake later. And if you look at the time constant is L by R. L is here how much? 30 Henry. 30 Henry is large inductance. 30 Henry in parallel with 30 and 40 ohm resistances. Parallel to 30 and 40 ohm resistances. This will give you 1.75 second of time constant, which is unbelievable in electric circuit. Means maybe in very large electric circuits, power system, that this might happen, power systems, but in circuits that we are talking about here, not. So 1.75 second is the time constant of this circuit, but hardly matters. We have to just solve the problem. Now we have got the inductor current. What we have to do is we have to find out the inductor voltage, and the inductor voltage is nothing but the voltage to the 40 ohm resistance. So the current through the 40 ohm resistance will be divide that inductor voltage by 40. So we will directly write current through the 40 ohm resistance is 1 by 40 V is L di dt. So it is again 40 ohm, 40 Henry. It was 40, oh no, 30 Henry. What I'm, okay, I will write it for you. What I'm doing is 1 by R times L di dt. So L is 30, that R is 40 times ddt of this. If you do this, you will get something. There is 3 by 4, 3 by 40, it becomes minus minus cancels out, 1 by tau comes out, and it remains the current through the inductor resistance. Okay. All right. The last question for today. Circuit shown in figure 10 determine VC at 0.8 second when the switch was closed at 0.3 second. Okay, so you see here there is a 10 volt 10 ut. So at t equals 0, this voltage source was activated, and at that time the switch was open. At t equals 0.3 second, the switch is closed. So what we have to find out is how much voltage the capacitor was holding at t equals 0.3. So capacitor voltage VC, now it's a RC circuit, so capacitor voltage looks like this. So it should be 1 minus e to the power minus t by tau, and the final voltage will be 10. So it should be minus e to the power minus t by tau, and this tau is for these two, this 8 ohm and 0.5. So this tau is how much? 0.05 farad times 8 ohm. So 40 on 0.4 second. So 10 1 minus e to the power minus t by 0.4. Now just before the switch is closed, the capacitor voltage is how much? 10 times 1 minus e to the power minus 0.3 by 0.4, which should be this much. So when the capacitor was holding this much voltage, the switch was closed. Now we have to find out before that this switch is closed, but that would hardly matter um, in our analysis, because All we are concerned about is the initial value and final value. So initial value of the capacitor voltage we know. Final value we have to find out. So how does the final circuit look like? Because as soon as the switch is closed, the time constant of the circuit changes and it goes into another dynamics. The nature of the dynamics is same, it's exponential, but the time constant changes. So steady state it will look like this: voltage here and 4 ohm. There is a 20 volt. We have to find out the capacitor voltage at this condition. I write it V. We don't even need to analyze the circuit, do we? There is 10 volt. So 10 volt gets divided by how much? 12 ohm. So it should be 10 by 12 into 4, and that much drop from the 20 volt side. So it comes out to be 20 minus 3.333. So something maybe 16.667 volt. This is V. Right? It's a simple circuit. The 10 volt is dropping across 8 volt, 8 ohm and 4 ohm. So how much drop is across the 4 ohm? So 20 volt minus that much is giving us the V. Now we know the initial and final voltage of the capacitor, and in order to find out the time constant, we can draw this. So what we are getting is 8 ohm and 4 ohm in parallel. So the resistance is 18 to 4 by 12. Somehow something it comes out. So what is the time constant? We will write time constant is a b by a plus b, 18 to 4 by 12 times capacitor is how much? 0.05. So some time constant you will get, put it here. So capacitor was where voltage was increasing like this. So initial plus what we did like that. Capacitor voltage is 5.276 plus 16.667 minus this times 1 minus e to the power minus t by tau. If you solve all of it, simplify this, calculate time constant from here, and then simplify. And what you have to do is, so you have been asked to find out the capacitor voltage at 0.8 second. So simplify this and put t equals 0.8. You should be able to get somewhere close to 16.4 volt. Okay, that's all for today. You tell me if you have any doubt in any question or anything into for today's class or any other class. If not, we will close today's session. No point of sitting here without any question or any discussion. Just tell me yes or no if you have any doubt. Rishi, I can't hear
I
you. I don't
couldn't
know if
watch the videos. Sir, am I audible?
yes.
Sir, in this week I couldn't watch the videos, all the videos which were uploaded, so I couldn't uh, answer the questions for today.
Okay. Thing is, these classes are not class. This is doubt clearing class. So
Mm-hmm.
it's recommend it's not for your learning, rather to get your doubts cleared. Although I have not solved a single doubt this session, I remember, because not a single question I got. I am only solving question in these sessions for the last 7 weeks, which is really unusual. NPTEL classes that I have taken in last 2 semesters were not like this. There used to be, I mean, lot of questions, lot of doubts, many good questions. I don't know, maybe this time the course is easy, although the responses are not like that. Anyway, so yeah, Deepak, do you have any doubt? We'll stop this session then.
No, sir.
Okay, then we'll stop this session and we'll meet next Monday, 6 p.m.